Hey everybody, welcome to the AC inductor portion of the class. It's going to be pretty fast. So let's just get started here. I'll pick up where we left off. I want to talk about inductors as AC circuit elements now. So here's a circuit with just an inductor and a current source. I'm sorry, an AC voltage source, alternating voltage power. So if we take a look at the voltage of the inductor, it's going to have to be the same as the voltage of the source at this point, right? Due to KVL. So what we'll do is we'll say that E minus delta VL, all of the instantaneous stuff, right? Whatever the instantaneous voltage is from the power, that's the instantaneous voltage across the inductor. So maybe you recall that an inductor voltage is related to the time rate of change of the current. So when the time rate of change of the current, that is to say the slope of the current changes, the inductor kicks and tries to resist the change. So what I want to do here is take a look. Now, if I start this voltage as I did before as a cosine, I'll have the cosine of omega t. That'll be, according to KVL, the same as the voltage across the inductor. What will happen, though? What kind of current will I be allowed to drive through this? Because ultimately, the current is going to oscillate as well, right? Because what's going to happen? The voltage is going to be the voltage is going to go through different slopes, right? It's going to go through different slopes, which means that the current is going to go through different slopes, and therefore di dt is going to change. So the voltage of the inductor is going to change, and it will allow more current sometimes and block current sometimes. So its effectiveness as a circuit element, the voltage across it will be changing. So if we think about it in this way, I take these two things and I say, well, okay, well, just knowing that the negative means that it's a sign. Well, I'll keep it in there. It's a polarity issue. So L di dt is going to be something like the peak voltage across the inductor times cos omega t. Okay, so what we have here then is you can see what's going to happen. There's going to be, with the capacitor, there's a differentiation of the charge. No, there's we had to integrate the current in order to get the charge. Well, what happened with the capacitor? I can't remember, but we had to integrate or differentiate or something. I can't remember what it was. But anyways, point being here, the same thing's going to happen. Oh, I guess we had to differentiate the capacitor. We integrate the inductor. There we go. Okay. So look, I'm going to get a di. I can integrate this thing. I can split the differentiation apart and do all this great stuff. But I think you can see that the current as a function of time is going to be proportional to some peak amount of current, right? Call it I. Well, no, I didn't call it I naught. Just call it I. Integral of the cosine is once again going to be the sine. Okay. And in this case, what I can do is I can actually rewrite no, I'm not going to do that. I'm not going to worry about that. I can rewrite the sine as a cosine, but it doesn't matter. Let's just graph it. Come on. Let's just graph this. I have a cosine for the voltage and a sine for and a sine for the current. Okay, so what I've got here. Okay, as a function of time, here is delta VL, and it's a cosine. Oh, I didn't leave myself quite enough room, did I? Which means you have to wait like 30 minutes for this thing just to do anything. There we go. Okay. I gotta wait for it to change. Okay, so the cosine, I'm trying, ooh, that last bit was kind of a little off in the frequency. I'm trying to draw a reasonable cosine. As you can see, I'm just freehanding it without actually trying to see if I'm going below the same amount as I'm going above or anything like that. And in fact, this peak is lower than that peak, and then my peaks are getting lower. All right, fine. Okay, so something like that. Whereas the current in the circuit now is a sine, which hopefully makes sense because look at what happens. The voltage of the inductor initially is large, right? So if the voltage of the inductor is initially large, how does that let current pass? Well, it doesn't. So no current must be passing in order to start. And that's exactly what a sine does, right? It starts off at the origin and goes up. So it will peak in the same way as it'll peak in the same way as this one. Oh, whoops. What am I doing? Like kind of, oops, and there I go again. I suddenly okay, suddenly got a lot more current in here. It didn't need to do that. It should be going down there, like not that one. Okay. So what's happening here is that the voltage of the inductor is large and not allowing current to pass. So the current is zero initially because the voltage of the inductor is blocking the passing of current. Now, as time goes on and the source starts to decrease its voltage, the inductor also must start decreasing its voltage, right? And they start dropping, and then you start seeing the current coming up as a function of that. So what's going on here is something kind of similar. Well, wait a minute. It's kind of similar as to what we saw in the capacitor. So in this case, I think I did it backwards. I was just looking because I was thinking, wait a sec, this is wrong. But last time I did I as the red one and charge was the Q. So voltage was basically the blue one and current was the red one. Oh man, I got it backwards. I'm looking at what I did this time, and I did voltage as the red and current as the blue. Okay, well, sorry about that. Point being here that the voltage is leading the current, okay? The voltage leads the current by 90 degrees in this case, so our phasor diagram for this one would look something like, okay, here's my voltage, doink, like that. So delta V L, this is the capital V because it's the full phasor. And then the current, so the current, remember, will be the voltage of the resistor. It's going to be back here. Okay. And then I would also say that the voltage of the resistor would be lying right on top of that thing too, right? Because that's how essentially we know what the phase of the current is. It's the same as the phase of the voltage of the resistor. Okay, these make a 90-degree angle because the peak of one was on top of the zero of the other. That means they're off by a quarter cycle, which is 90 degrees. So what we're getting here is that in the inductor case, come on, wake up. Can you pour coffee on the computer to make it wake up? Okay, so in the case of the inductor, the voltage leads the current, and it's the Eli case. Okay, so these two little mnemonics are super cheesy, but Eli Ice is how you remember which way the phase relationship of the voltage and the current in AC circuits, which way these things are, right? Compared to ice, where current was in front of the voltage by 90 degrees for the capacitor, all right? And we kind of talked a little bit about that. And the same thing's happening here with the inductor, but just the other way, right? Because the inductor is first initially responding to the power source trying to push charge through the circuit. It's saying, here, I'm the inductor and I'm sitting here, nothing's happening. And then all of a sudden, this thing over here is suddenly trying to push charge. And I'm going, hey, wait a sec, man. No, you can't do that. Stop. And all of a sudden my voltage kicks up and I start blocking the current. And then as the voltage, so in a DC case, what would happen? What would happen is the voltage would just stay still. And eventually the inductor would go, oh, no more changes. Okay, all right, go ahead. Because what you found in the DC case is that the current slowly went up, right, and flattened off. And it's the slope of that current that causes the voltage of the inductor, right? So here, when you initially have nothing happening and suddenly you're trying to hit it with some current, it freaks out and goes, what are you doing? And it stops the current from going. And then it starts to back off its push, which means it's changing its voltage. Okay, so I start changing my voltage. And as I start changing my voltage, that allows the current to start flowing, right? And you can see from the graph over here, boy, even if you let the thing sit, it doesn't wake up. Okay, so you can see from the graph here that in fact, because of the voltage of the inductor, the current is going to be peaking right at the time when the voltage of the inductor is 0. That makes sense, right? So what really I should do in this circuit is, if I were to, if I want to kind of just put in a little bit, you want to put in a little bit of a resistor here, not a very big one. Let's just call it little r here, so that you can imagine, look, what's going on here. As you don't want to always say that the voltage of the inductor is getting, is matching exactly what the voltage of the source is, okay? Because I got to have a little difference there. So what's happening is, as the current starts to flow, I start getting this voltage up on the resistor, right? So as the voltage on the resistor starts to kind of go up, the voltage of the inductor starts to drop, and that's right. That's how this whole thing works. The inductor is dropping in voltage. The dIdt is starting to peak. It's starting to get to a peak, and right as it peaks, the slope is 0, and therefore the voltage of the inductor is 0. So that's the situation here with the inductor. So that's the phasor. That's the phasor diagram of the inductor. So what I want to do here is think about what happens if I stick an L and a C in the circuit together. An LC circuit. So what I have is, let's imagine that I have a charged capacitor, switch, inductor. Okay, I'm going to put no resistor in this circuit for right now. What's going to happen? Okay, so I'm going to start with a charged inductor, a charged capacitor. Sorry. I'm going to start with a charged capacitor, and then we're going to close the switch at, for lack of a better time, t equal to 0. All right, so here we go. We're going to do t equals 0. Capacitor charged, switch closed. All right. Okay, there we go. So delta V of the capacitor is large and it starts driving current. So the current starts to go, wee, like, look at this. And then all of a sudden the inductor says, what are you doing? And the voltage of the inductor kicks up, okay? So when this happens, by the time the inductor starts to kick its voltage up, the voltage of the capacitor is starting to go down because it's pushing charge, okay? So the energy in the capacitor, let's do this. Let me do a little bar chart here. Okay, so here's the capacitor. There's the energy of the capacitor initially, right? This is T equal to 0. And then what starts to happen is as the capacitor starts to discharge, it's losing its energy stored because it's pushing charge into the circuit. But as you push charge into the circuit, what happens? Well, the current starts to try to go through the inductor, which causes a B field in the inductor, right? So the B field in the inductor, I don't know which way the coil is going here, but let's just suppose it's going like that. The B field of the inductor starts to store that energy with the current going through it, okay? So here what's going to happen is I'm going to find that there's some energy stored in the inductor. The capacitor is not fully discharged yet, so there's some energy stored in the capacitor. Okay, so now as you keep going, what you find is eventually the capacitor is fully discharged and the voltage of the capacitor is 0. The voltage across the inductor is also 0, has to be because they match because of the loop rule. The voltage of the capacitor is 0 because it has no charge. The voltage of the inductor is 0 because there's no more change in the current. It's at its maximum current right now, which means all of the energy in the circuit is held inside the B field of the inductor. The B field of the inductor, right? The current peaks, there's no change, and then it starts to say, hey, what? There used to be a change in the current. The current used to be going up. And so the inductor goes, hey, wait a minute, I want to keep that current going up. So it starts dumping its energy into trying to keep the current going, right? So it keeps the current going. And what happens then is it starts to push the charge back onto the capacitor. So the capacitor ends up oppositely charged. So I get another energy like this, where now I've got energy stored back in the capacitor. I've got a little bit of energy stored. The inductor is using its stored energy in the B field to push the charge. That charge is then going into the circuit and recharging the capacitor, but its polarity is now flipped. Okay. So now you go into the thing and you say, okay, I've got the capacitor as the inductor kind of fully divests itself of all of its energy. It realizes that the current is stopping, right? The current's going down and down and down because the capacitor is just sucking up the charge and blocking more of the current from flowing. So the inductor realizes, wait a sec, the current is now going to 0, right? It's at its maximum slope, which means the voltage of the inductor is at its maximum, trying to push more charge, but there's nothing left for it. And the capacitor is fully charged, which means their voltages are matching, which they have to because they have to match in the loop. But all of the energy is now stored in the oppositely charged capacitor. In reverse polarity. Right? So the charges come into the inductor, has caused the inductor to kick, stored a little bit of energy in the B field because the current is flowing through it. As the current goes this way, it starts to push positive charge onto this plate, which initially neutralizes the negative charge that it had, and then goes over. So then what happens is you get this oscillation, right? If I have no resistance, then what I get is an oscillation of the energy from the capacitor storage in the E field to the inductor stored in the B field, and back to the capacitor in the E field and back to the inductor in the B field. So I'm getting this sloshing of energy moving back and forth. This is an oscillatory electrical circuit, which means you can build an electrical analogy to a mechanical oscillator. In other words, if you have a spring and a mass, or a complicated set of something like, I mean, the first thing that comes into my mind are like a suspension system, right? Of a bicycle, of a motorcycle, a car, a truck, whatever. If you're going to have shock absorbers, then you need to put a resistor in here to damp the oscillations. You set a frequency, and the frequency of oscillation here you can set by the values of the L and the C. Okay, and so you can model any oscillating mechanical system with an electrical analogy, which is way cheaper, right? These, I'll just go buy an inductor. They're like, what, 5 cents? Well, no, they're more than that. They're like $2. But capacitors, same thing, right? A lot cheaper than going to buy a huge coil spring, a bunch of leaf springs, a live axle, and then a bunch of gas shock absorbers or something like that. You know, it's so you got a good opportunity here to just do a little bit of, what's going to happen if I tune it this way, if I tune it that way, if I up the damping by increasing the resistance, if I lower the damping. This is a really great problem to explore. And I'm sorry that we don't have more time to explore it, but I will leave you with the idea that if you remember from 4A, you have a mass with a spring, and it has an oscillation frequency because its energy is going from the kinetic energy of the mass into potential energy stored in the spring, back into pushing the mass, back into compressing the spring or extending the spring. You'll see that this is the exact analogy electrically of that spring mass system. The capacitor is obviously acting like the spring, right? It's storing the energy as potential, which means the inductor is acting like the mass, right? Which kind of makes sense, because when you push on something, not so much that it resists you, but one of the things you might have run across is that mass resists acceleration. That's not really true. It doesn't actively resist it like an inductor does, but an inductor basically just the mass is just standing in your way, right? You have to push harder on bigger masses in order to get them to accelerate. Same thing happens with the inductor. It's just kind of inertial, right? It wants to keep this thing going. Okay, examine the idea of the inductor as we've spoken about it. When something first happens, it goes, "Hey, what? I don't want to move," right? Because you're think about the analogy of di dt with the speed, right? If you say, "Well, wait a minute," or di dt with the acceleration. So it says initially it doesn't want to accelerate very much when you're pushing a little bit on it. Then you start pushing a bit harder on it, like you have an AC voltage, right? I'm going to push harder on it. Then it goes, oh, okay, it's going to overcome that. You're going to get some grudging acceleration, like you're going to get some grudging current through the circuit with the inductor. So it kind of is inertial in that sense. And so you can go through and play with all sorts of differential equations here, but you know, this is a great application of the damped what am I trying to say? The damped whatever this is, oscillating system. Man, I can't think of what I'm trying to say. Anyway, the math people have a nifty little word for it. Ultimately, they can solve the equations, which is great, but they have no idea what they're talking about when it comes to applying it. So you can talk a little bit about the resistance, right, in the circuit here. If I were to put a little resistor here, now you can talk about that thing as being the energy dissipator, and ultimately, right, you'll see the size of the energy bars slowly decreasing, or you'll just see them be the same size with the thermal energy in the resistor and the I squared R of the resistor increasing, right? Inside the proportion of it increasing inside the same size bar. And therefore it's losing the energy that was sloshing back and forth to heat in the resistor. And that's exactly like damping an oscillation. You can also, because you have an R in there, you could also then put in an active source and have a forced oscillation, and you can do a forced and damped oscillation. So these are really amazingly rich and wonderful things to explore, because it really gives the mathematics a basis in life, which is fun. I'm not saying you have to. Mathematics doesn't need a basis in life. It just is. But I wish that we had more of an opportunity to play with it, because in math, you don't get to play with things very much. And we are mostly just like little kids. I just want to play around with this stuff and say, oh, what happens if I do this? Where does it go? What if I increase the resistance? What if I put in a power source? What if I vary the frequency of the power source? What happens to what if I have a frequency of a power source which is different than the frequency of the oscillation? Oh, well, interesting. What if I increase the damping? So you can just play with this and have fun. And sadly, we just don't really have time to explore with that. So there's that. You can imagine then that what happens when you have a full RLC circuit powered by AC voltage. Interesting things happen. So instead of busting out lots of math to do this, let's just look at the RLC circuit in the phasor analysis model that we've kind of developed here. Okay, we already know that I've got an L and a C, which means I'm going to have an Eli and an ice, and I have an R, which means I'm going to have a current. Okay. So suppose that at some point I have a current in the circuit and I have two voltages. All right. So let's suppose that I have this. Let's suppose that I have this circuit where what I'm going to do is I'm going to say, okay, I have, let's suppose I have, can I stop with the neon yellow highlighter here? Can I do something different with that? No, it doesn't look like it. All right, so I'm going to do blue. So blue will be, say, the voltage of the resistor. Let's say that's here. You know what? I don't want to do this with a circle. Okay, sorry. Can I start all over? I just want to... I don't want to do this with a circle, because I'm gonna have voltages of different sizes and stuff like that, and it's gonna get kind of confusing. So let's just do this. Okay, so here's delta VR. Okay, and that means it's also the current. That's the direction. That thing has the phase of the current. Okay, so what happens if I take a look at Eli and ice? Where is the voltage of the inductor? Well, if that's the voltage of the resistor and that's the current, then the voltage of the inductor is going to be over here. I didn't like that arrow. I'm going to try that again, but that means I have to wait like 10 minutes. Hold on a sec. Let me get rid of this freaking thing. Perfect. Okay, for no reason at all, I'm just going to draw a really large, delta VL here. Okay. Okay, so now here's a delta VC, and for just some reason, I'm going to draw that less. Okay. So, oh, let me erase my, okay, so there's the VC. So these things are at right angles to each other, like that. The voltage of the inductor is leading the current. The voltage of the capacitor is lagging the current. And then the question comes in, well, what's the voltage of the power source doing? Where's that? Well, that's not an easy question, but notice that it has to be such that right, if I loop around an RLC circuit, I didn't draw an RLC circuit, sorry. If I loop around an RLC circuit, nice. Okay, if I loop around an RLC circuit, then KVL tells me that the voltages have to add. So I would have V, suppose I have minus delta VR. Notice that that's the instantaneous. I don't know, minus delta VC, or no, plus delta. No, I'm going to do minus because suppose that it's going that way. So minus delta VC plus delta VL, I don't know, it's equal to 0. So I loop around these things and they all have to add up, right? What does that mean in this case over here with the phasor diagram? Okay, what it means is that you add these vectors. Okay. So, okay. It means you add these vectors. So the VC of the capacitor is opposite the VL. Okay, so I'm going to take the VL of and the VC of the capacitor, and it's only about that big, like that. So since they're aligned directly on a line, I can just add them straight, which means the total, this thing here, is VL minus VC. All right. Now, if I make my parallelogram right there, that must be the voltage of the circuit. I mean, the voltage of the power source. Okay. Because ultimately it's just you're adding the rest of these things and looking at, well, okay, I'm just doing phasor addition, right? These voltages have to add up to give me the voltage of the source. Okay. So all sorts of fun things happen because there's an angle here between the voltage of the source and the current in the system because of the way that the capacitor and the inductor are kind of blocking and assisting the current. Okay, let's try this again. Okay, so at a resonant circuit, if I want a resonant circuit, what characteristics am I going to notice about this phasor diagram? The resonant circuit, if I go back to an LC circuit, first of all, the voltages are going to be the same. Delta VL is going to equal delta VC, right? So that, well, negative, right? I mean, okay, so if I do the phasors, that they're opposite, right? But I mean, the magnitudes are going to be equal, right? So if the magnitudes are equal, then I could, no, I don't want to say that. I don't want to do peak. Sorry, I'm going to take those bars away. Let's say instantaneous. Okay, so they're out of phase. Okay, so one's pointing one way, one's 180 degrees opposite, but they have the same magnitude. Okay, once they have the same magnitude, if those vectors are the same size and pointing in opposite direction, what happens to the angle phi right here between the current in the circuit and the voltage of the power source? That angle goes away. In other words, the voltage of the power source lies directly on top of the current in the circuit, which is what we expect because that's a DC situation, right? The current always, or the voltage of the source always drives the current. But look what's happening. You have other things in this circuit which are impeding and blocking and adding to the current, even despite what the power source is doing. Okay. So they're reacting to this thing and going blah 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 do 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 do, right? And they're doing other things to muck up the phase of the current with the voltage source. Okay. You'll also notice that at that point, the current in a resonant circuit is its highest value. Okay. You'll also notice that that's its maximum value because basically at that point, the two components, the current, the capacitor and the inductor, are essentially, their effects are balancing one another, right? When one's pulling, the other one's pushing. When one's pushing, the other one's pulling. So they're kind of doing the opposite things, which leaves the voltage source to be able to just drive the current, and that means you get a peak in the current. All right. So anyway, that's pretty cool. I think that that's all we really need to worry about here with AC circuits, and I'm sad, but I'm excited for you all to either find out more about this or sit back and bask in the glory that you have learned whatever it is that you're going to learn about these things. So anyways, happy rest of your day, folks. And our last video is going to be a wrap up of the Maxwell equations. See you then.